All right, well, thanks everyone for being here, and I'm excited to tell you about some of the work that we've been doing here at the university in the 3D printing space, specifically for neural regeneration devices for spinal cord therapy. So this is a big problem, a big challenge, and we're tackling it head on with our 3D printing technology using custom-built printers that we build in our research group in the Department of Mechanical Engineering. Spinal cord injury is a devastating injury which can affect about 12,000 people in the US every year. And you've heard of these folks in the news. This can affect celebrities. Christopher Reeve, who was thrown from a horse, and unfortunately he was a quadriplegic for the last 10 years of his life. And Sam Schmidt, who was an IndyCar driver, and actually he's still alive, and he was the person who funded our research, got this project started, believed in what we were doing, and allowed us to actually make major advances in terms of 3D printing neural regeneration devices for spinal cord therapy. And the spinal cord injury is a traumatic event in which someone is incapacitated. They can lose the ability to walk for the rest of their life, maybe also lose the ability to move their arms as well. It's an irreversible damage, and these people are told that there's nothing that they can do. Well, we believe here at the University of Minnesota that there is something we can do, and so we've been really pushing this area because it's such an important area. Now, in order for us to address this, we first started with a problem that actually affects more people than the spinal cord injury, and is a slightly easier engineering problem than the spinal cord injury, but is a stepping stone toward that, and still a very critical problem because it affects so many people, and that is the peripheral nerve injury and repair. So basically the way your nervous system works is you have your brain and your spinal cord, that's the central nervous system, and then you have nerves which come out of the spinal cord into your arms and legs, and these nerves basically, there's a two-way communication system. You can think of it as a bundle of electrical wires where your brain sends signals down out to your hands and feet, and that controls motor function. And if you touch something like I'm touching this object here, then that's sensory information which goes back to the brain. So you have two-way communication, motor out, sensory back in. And unfortunately, this communication system can be damaged in several different ways. For example, you can be, a soldier can have a battlefield injury, you can be in a car accident, you can have a degenerative disease where your nerves shrivel, and you lose the ability to walk, you lose the ability to feel. You may have family members who this affects, these peripheral nerve injuries, and there's about 200,000 peripheral nerve repairs annually in the United States. And so the question is, what can be done to repair the damaged nerves, restore function, restore the ability to walk, restore the ability to move and feel as well in these patients? That's the goal. So the gold standard for doing this now is something called an autograft. So you think about, let's say, a peripheral nerve. You make a cut in the nerve, let's say a nerve in your arm, and now you have lost communication because of that gap between the proximal nerve, which is still connected to the spinal cord, and the distal nerve, which is now not really connected to your body anymore, and the body starts to eat away. So the question is, how do you bridge this gap and restore function again and restore communication across the gap that was severed? So the gold standard for doing this, the autograft, is basically they take a piece of healthy nerve tissue somewhere else in the body, and they graft it into that gap, and that restores the communication. But the problem is they need to sacrifice healthy nerve tissue somewhere else in the body. You need a second surgery to remove that nerve tissue, and then you may have loss of sensation or loss of motor function in the place where the nerve came from. So you restore this function, but you may lose function somewhere else. So there are, let's say, cadaver donors which may donate nerve tissue to you. This is called an allograft, where the tissue is actually coming from someone else. The problem with the allograft is that since the tissue is coming from someone else, your body may reject it since it's not your own tissue, and there's an immune response by the body against that foreign piece of nerve tissue there. So one of the another option is the nerve guide conduit, which is a synthetic system where you don't have to rely on biological tissue from yourself or for someone else. It's a linear tube, a polymeric tube, where you can suture the two ends of the nerve into that tube, and that provides a physical guide to guide the regrowing nerve from the proximal end to the distal end, and hopefully restore function, hopefully restore the ability to move, hopefully restore the ability to feel again. The only problem is that these nerve guide conduits almost uniformly are short tubes. They're linear tubes. They're about 1 centimeter in length. And so you think, let's say you're in a car accident, how often is the injury going to be just a short, small 1 centimeter gap between the nerves? We need something that's more complicated than that. We need something that can do long gaps, let's say 6 centimeters. We need something that can branch the way your nerves branch in the body. We need something where we can maybe incorporate functionality into the guide, whether it's electrical stimulation, whether it's growth factors, nerve factors, to help the regeneration process. That's what we need. So the tools for doing this are limited, but we have developed a tool in our group, a 3D printing system that's built from scratch that can actually print many different types of materials. So I think many of you now have probably heard of 3D printing or even used a 3D printer where you can print a hard plastic object layer by layer into a three-dimensional structure. And the beautiful thing about that is you can make that structure any type of shape you want, even complex 3D shapes. However, you're limited by the fact that it's a hard plastic, which is not something you necessarily want to implant in the body because your body is soft. It's something that has limited function. And so if you can print materials, let's say, that are soft, materials, let's say biological materials, if you can print electronic materials, that would be revolutionary in the 3D printing space. And in fact, the printer that we build can do all three of those. It can actually print almost any type of material, any type of functionality, and we're doing all kinds of amazing things with it. This being one project of many in this space. So one of the things that we did, one of the ideas we had, is can you actually bridge a branched nerve structure? So look at not just a short linear tube, but actually create a conduit that branches just like the original nerves do. So for example, let's say you have loss of motor and sensory from the branches. Now you can restore both motor and sensory function in the body, restore that two-way communication instead of just one-way communication. And the way we do this is we use a combination of 3D printing and 3D scanning. So we can scan the actual tissue that was transected, the actual nerve tissue, get the exact geometry of that nerve tissue, and then print a guide which is anatomically accurate that can then be bridged into that gap to help restore function. And so we actually have done this in rats, and we looked at the sciatic nerve, which is the major nerve in the lower leg of humans and rats. And we looked at a branch point where as the nerve branches down, travels down, you have mixed motor and sensory, and then it branches off into motor on one side, sensory on the other. And we cut that tissue out at that branching point, so the rat then loses the ability to both walk and feel due to that transected tissue there. And then we can do a 3D scan on this tissue, create a 3D computer image, 3D computer model of the nerve tissue that was transected, and you can see it branches just like the original nerve tissue did. It's an exact scan, 3D scan of that nerve tissue. And then now we have it in a digital format in our computer, and so we can feed that information into the printer and print a custom guide, as you see here, which follows the exact topology of the original branching structure that was cut out. Now, this is a silicone guide, so it's a soft material silicone, which actually cannot be 3D printed using a conventional 3D printer, and yet it's a soft, implantable, biocompatible material, extremely useful material. And as you can see, not only are we printing the silicone, we're printing these red and green droplets inside, which are actually growth factors, biological growth factors that help direct the regrowing nerve as it grows. So our printer can handle many different types of materials, including even printing biological materials, biological functionality into the guide to sort of recapitulate the original environment of the nerve. And so we actually have implanted this nerve tissue, this nerve guide, into the transected gap there, that bifurcating injury where we cut out the nerve tissue. We then implanted the guide there, and again, we cut this out of rat, so the rat actually, in the rat's hind left leg, could not walk for 2 months because we cut out that nerve tissue. Then we implanted this guide, and 2 months after we implanted the guide, as you can see here, you can see that the rat basically can walk just like he could at the start. And he can feel too, because we're restoring the sensory, the sensory nerve there. So the nerve basically regenerates itself by virtue of the fact that we're providing a custom-built guide that's being implanted inside this rat. Now, this is the peripheral nerve injury. The advantage of the peripheral nerve, so this affects more people because your peripheral nerves are exposed. And so, again, it affects 200,000 people. And as long as we provide this silicone scaffold implant into that transected nerve injury site, then the nerve will spontaneously regrow through the scaffolds, and you can direct that growing nerve and then restore function, as you see here. Now, the spinal cord is a trickier animal. So the central nervous system, the spinal cord, is a much more complicated problem. So first of all, I should mention that, again, this is a debilitating injury, and it primarily is due to accidents. And therefore, it primarily affects young men. And they get, let's say, in a car accident, and they shatter their vertebrae, they injure their spinal cord, and depending on where that injury is, that'll determine whether they can walk again for the rest of their life, and whether they can even move their arms again for the rest of their life. So the question is, there's no current effective treatment, so is there something that we can do to provide a new treatment in this space based on what we learned from the peripheral nerve injury? So it turns out that unlike the peripheral nerve system, where the nerves spontaneously grow, the spinal cord is actually much trickier because of the fact that the axons, which are your communication signals which come from neurons, which are the cell bodies, the axons which form the nerve bundles do not spontaneously regrow in the spinal cord. And the reason for that partly is due to the fact that you have a spinal cord injury. So obviously there's a bruise there, which may impact the ability for those axons to regrow and communicate with one another and travel down the spinal cord again. However, even the spinal cord itself tends to have factors in it which are inhibitory toward nerve regeneration. So we have to overcome this. We not only have to provide a scaffold, but we also have to provide the axons and the cells that can overcome the fact that the ones in the spinal cord are not regrowing. And so we have to now 3D print not only the scaffold, but we have to print neurons. And neurons are very delicate cells. So the neurons in your brain are the same in your spinal cord. It's the axons that travel down, those are the nerves, and then travel out through your body. We have to provide those cells, we have to provide the cell bodies there of these delicate cells and print them into our scaffold in order to start the regeneration process. Now, the beautiful thing about being at the University of Minnesota is that the engineering program is directly across the street from the medical school. So you don't have to go very far in order to connect with doctors, in order to connect with biomedical engineers, in order to connect with cell experts and bioengineering faculty, and tackle these big problems at the interface between the medical and the biomedical and the engineering. And in fact, our collaborator, Dr. Ann Parr and Dr. James Dunn, they helped us with this by their spinal cord experts, and they provided us cells. And they have this amazing technology where they're able to take skin cells from someone and reprogram them back into all-purpose stem cells, which are basically cells that can turn into any type of cell in the body. And then they program those to become what are called neuroprogenitor cells, which are a type of stem cell which preferentially differentiates into neurons, which are the cells that we want to, which sprout axons and then form these communication signals again. So the point here is that the body won't reject these cells because it's coming from your own body. And it's not coming from something where you have to take cells out of your spinal cord. You're taking the cells from your skin and then converting them into the cells that are like the cells in your brain. It's amazing. And the cells that we used in this project were in fact human cells. They weren't animal cells. These are human cells that we're printing here. And so as you can see in this video here, we're printing the scaffold similar to what we were printing before in this layer by layer process, but this scaffold actually contains these grooves within the scaffold, and into these grooves, so right now we're printing the silicone, and then into these grooves we can actually go and print the cells, that's what you see here, into those grooves and provide not only the scaffold this time, but also the cells that are needed to do this regeneration, because the cells in your spinal cord don't spontaneously do it, unlike the peripheral nerve system. And so this is, we were amazed that the cells actually do survive the printing process. And in fact, 75% of the cells of these delicate neuron cells survive this printing process. Of course, we had to do a lot of ink optimization in order to make this happen, but eventually we were able to get to a point where 75% of the cells survive. And in fact, we can then differentiate these cells into neurons, which then sprout axons within the scaffold, and these red dots that you see are the nuclei of the neurons, and these green bundles that you see are the axons, which are sprouting from the neurons down the scaffold, and this is where the communication signals are as it travels down the scaffold. So this is actually the first demonstration of 3D printed human neuronal stem cells, which differentiate into neurons with extended propagating axons in a 3D printed scaffold. And this was published about just a little over a month ago, and we received an amazing response from it. And I'm getting emails on a weekly basis from people who do actually have spinal cord injury who are really hoping that this is the future technology to help them. And as you can see here, what this image is showing is that not only are the cells alive, not only do the cells differentiate, not only do they sprout axons, but the blinking lights that you see here are actually the cells communicating. So these are calcium-dependent action potentials, which is basically the way that the neurons communicate. And every time you see a blink there, that's calcium going into the cell, which is basically the way the cell communicates and turns from the calcium ion to an electrical signal in order to propagate signals down these scaffolds. And this is 2 weeks after we printed the cells, so they're alive actually for several weeks inside these scaffolds. And so we really believe we're actually starting now to implant these in rats to see if we can actually restore spinal cord injury in rats like we did with the peripheral nerve guides. And we're really hopeful that we can. And this is just a start here because in the future maybe we can incorporate electrical stimulation, other types of factors to help this regeneration process and help people walk again. That's the goal. So this, again, even though this is a beautiful project, it's actually just one of many projects that we have ongoing in our group. So we have a great group of people here working on lots of different projects, lots of projects in the biomedical space, heart repair, cancer studies, spinal cord repair, printing electronics on the skin, printing flexible electronics. We're doing many amazing things with these 3D printers, bionic eyes. You may have seen that 2 weeks ago, 3D printed bionic eyes. And we're excited where this technology is going to go, and we're excited to be here at the University of Minnesota pursuing these new approaches. So thanks a lot.